Okay, so it's my pleasure to introduce Anh Vinh from Vietnam National University and Vietnam Institute of Educational Sciences. So today he's going to talk about expanders in finite fields. So thank you very much.
Okay, so thanks organizer and thanks Thắng for inviting me to make a presentation. And as I mentioned and some other mentioned as well, I mean, unfortunately, we cannot gather in Moscow, I mean, to discuss about math, but anyway, I mean, we still can make it happen. And the online conference, so I will continue with my talk, and I will spend 30 minutes to talk about expander in the finite fields. It has some related to other presentation in the section as well. I can saw, I mean, from the presentation of Dong of some, I mean, some relation between the different problems, but I want to look at only the expander in my presentation. So the contents of my presentation will contain 3 parts. The first part to mention about what is the expanders, why it is interesting, why we want to study about that. And we talk about the second wave of the result. The first wave is back, I mean, to 2004, and the second wave is in the last recent year. So the expander is a function, and I mean, we can imagine it simply like when you apply to a set, you want to increase the size of the set. And if you can increase the size of the set by a function, then it is called an expander. And in the presentation, we focus on the expanding polynomials. And the precise definition is if you have a polynomial f, and it is called the expander, if you apply on the sets a1, a2, ak with the size of the n, then the values of the function will have the size bigger than n. And the row rate of the expander will be defined by alpha, and alpha will be greater than 1. And of course, we want to find, I mean, the strong expander. It means we want alpha as big as possible. Okay, so one of the first results that I want to mention here is the two-variable expander. And it's not surprise when all of the two-variable expander, polynomial expander, if they don't have the additive forms or the multiplicative form, then it will be the expander. So let's think about this in a, I mean, easier way. So if you're looking at the sum or the product, right? If you look at the polynomial x plus y or x times y, it is not an expander. And it's kind of what I can say, expectable. People can expect that if the polynomials are not of that form or are not created by that form, then it will have the row rate than, I mean, linear form. So the first result by Elocas and Ronai in the Journal of Combinatorics Theory series confirmed that if you have the two-variable polynomials that do not have the additive form or multiplicative form, it will be the expander. It will have the row rate greater than 1. And a quantitative version of that result confirmed that actually the row rate is quite good. It is 4/3. So it means if you apply the two variable polynomial with the do not have the form additive or multiplicative forms, then the set of the size will increase at least by a over to 4/3. And if we look at higher variable expander, the three-variable expander, then the result by Schwarz, Solimosi, and De Zilf in Journal of Combinatorics Theory series in 2013, 12 years later, right? Then only non-expander three-variable polynomials over R are of the forms, and it is also expectable. It is expected it will have the form of the linear or multiplicative forms. And later on, Ras, Sarius, and De Zilf, they provide quantitative versions of this result with the alpha equal to 3/2. So basically, they can classify 2 variable expander and 3 variable expander and provide a quantitative version for both results. For the expander, the most interesting case will be the second variables and the 3 variable. And the medium's interesting case will be the fourth variables. And if we have the higher variable polynomial, the higher chance it will be the expander, and the growth rate will be much higher for that. And now we move to the expander over the finite fields, and we will go back to the first wave of the result. And it's back to the seminal paper by Borgen, Katz, and Tao in 2004. And the statement is stated for the sum product estimation. So as I mentioned at the beginning of the presentation, if you look at the sum or the product, the growth rate can be as small as a linear. For example, if you taking the arithmetic progression, then the sum will have the similar size with the original set. It's only double the size. And if you're taking the geometric progression, the size for the product will be about 2 times of the set. So we expect that if the polynomial is not of the additive or multiplicative structure, then it can be an expander. And the first result given by Borgen, Katz, and Tao for the sum product estimation confirm in this case. It means if the set A is not too small or it's not too big, it means it's not cover the whole set, or it's not only the small subset of the field, then either the sum or either the product will be bigger, much bigger than the original set. And it is one of the first expander result over the finite field. And for the quantitative versions, GRF, so that if the set A is large enough, it means here when we define the large, it's over than the half of the size of the field, right? So A is much bigger than P over a half, then the sum of the product will be much larger than the size itself. Okay. And for the small set, there are several results by Garaev, Katz, and Sen, Borgen, Garaev, and Rudnev. And the most recent results is the maximum of the sum of the product sets is much larger than A over 1 plus or 1 over 11. So you can see, epsilon will be more than 1 over 11 in this case. Okay, and some general results. But before we move to more precise statement, let me recall the definition for the expander. We classify expander by the growth rate, and the strong expander is when the case if we have the size A and you apply, if you have the set A and you apply the function f to that set, you can cover most of the field except only few exceptional. Then the function f will be called the strong expander. And you call it the moderate expander if you apply the function and the image of that function will cover the positive proportion of the fields. Then the function will call the moderate expander. And we call the function f either weak expander if you can find the threshold. When you apply that function, the size will increase. Will become bigger than the original set. And the interesting point here is we need to classify which expander is strong, which expander is moderate, and which expander is weak. And we want to find the relation between the epsilon and delta. There are some strong results. The first weak expander, the 2 variable expander, is given by Borgen. He showed that x squared plus xy is a two variable expander. And when you apply to the set, it will expanding the set. And more quantitative result, the fxy, when you can separate 2 functions, fx and plus x to the k gy, then it with a certain exceptional for fx and and gy, then it's also the expander given by Hennecat and Henry Barry. And for the moderate expander, Ilya, right? I mean, the result is x times x plus y is the moderate expander. And when A is bigger, much bigger than P over 3 over 4, then the image of the function will cover the positive proportion of the field. And it can be extended for most of the two variable expander, and the result is given by Tao in 2015. Fxy is a moderate expander for if f is not of the form with the additive or the multiplicative structures. Again, I mean, for most of the case, if f is not of that form, the polynomial not of that form with the additive or the geometry multiplicative structure, it is expected that f will be with the expander property. So Tao proved that Fxy will be moderate expander given that A is bigger than P over P 7 over 8, and the polynomial is not of the form with the additive or multiplicative structure. Okay, so let's talk about the threshold epsilon equal 1 over 3. There's some result in the first wave when given by various authors, and Hart Iosevic given some expander for 4 variables with the threshold 1 over 3. Related result, and it's called the volume of the set or the Minkowski distance, right? And more general result when we're talking about the 3 variables of the form A plus f of AA, where f is a 2 variable polynomial, it's also the expander, the moderate expander, given that A is bigger than P over 2/3. And we want to, I mean, have a better threshold. We want to break the 2 over 3. It has been break, but at that point, I mean, it is the result. And most of the result here are given using the Fourier method. The threshold 2 over 3 is broken to 3 over 8, but it is only for 4 variable expander. And it has been proved that several types of the polynomials, for example, xy plus u minus v squared, fx plus gy plus uv, and so on, they are moderate expander with the threshold 3 over 8. And it's notable that there's some related expander with the threshold 3 over 8. For example, the result by Pechidis, he showed that the Minkowski distance is also the moderate expander. And there's some rational function. For example, xy minus u over x minus v, or y minus x over u minus x. They are moderate expander with the thresholds smaller than 3 over 8. However, I have to note that for that it is a rational function, and we don't have any moderate polynomial expander with the threshold smaller than 3 over 8. So it will be interesting to see some of the polynomial with the threshold smaller than that. And the last result doesn't belong to the first wave, it belongs to the second wave. And they are based on the more advanced technique based on the incident given by the root net. So I think it's a good transition to move from the first wave to the second wave when we mentioned about the incident between the point set and the plane sets over the space. And the result is given by rootnef, and I think it's very familiar with most of the participation in this seminar, because it has a lot of application, and I will not go into the details, but basically it given an improvement on the upper bound of the incident between a point set and the plane set over the finite field space and any field in the space. There's only constraints about the size of the point set and the maximum number of the collinear points that we also need to check whenever we want to apply the incident of rootnef. And there's some straight application from that theorem. Rudnev given some application in his paper as well. And the first one is proving to break, the threshold for the expanding polynomials xy plus ct. And here the result for that, the size of the set a times a plus a times a will be bigger than the minimum size, either the field, the size of the field, or a over 3 over 2. And related result, you can see here, by Roger, Newton, Rudnev, and Skadov for the max of a plus a and a times a, the estimate, some broad estimate, and also the same paper, a plus a times a, right? And you can see very similar about for that. Okay, so basically it's given some 3 and 4 variables over the finite fields, and this result improve the previous result. Okay, so the question is whether we can classify on 3 variable expander over the finite field. And the technique here is we apply the Rudnev incidence, and it is a joint result between Thắng, Brazils, and myself. And it's not our expectation. If the function does not have the form of the additive or multiplicative form, then it will be the expander. The point is whether we can prove that it is strong expander or not, or at least is the moderate expander. And the result here is, if f is not of the form with the additive forms, of course it cannot be of the multiplicative form, because we only focus on the quadratic polynomial, the degree 2. So we can prove that the image of the function apply on the 3 sets A, B, C of the size n's will have at least the size n over 3 n to 3 over 2, or it will cover the positive proportion of the field. And some of the application of this one, for example, when we applying for the quadratic polynomial x minus y squared plus z, then we can recover some of the result. For example, a plus a squared will have the size at least a to the 6 over 5, or the maximum of a plus a, or a square plus a square will be at least a square a to the 6 over 5 when the size of a is smaller. When the size of a is bigger, we can use the straight incident in the first wave. Okay, or we can prove the equidistant problem for the product sets for general case, and we have this result. Okay, so let me give a very quick outline of the proof. We will not go into the detail, and it is the standard way to apply the Rudnev incident in this type of problems. So we want to count the number of the solution of the equations f(x, y, z) equal to f(x prime, y prime, z prime). And by applying the Cauchy-Schwarz inequality, we can have a bound for the number of the solution, and we will have the inequality a square, b square, c square is smaller than or equal to e times the size of the image of the function f. So in order to give a lower bound of the image size, the size of the image of the function, then we need to give an upper bound for e, right? Upper bound for e. Then we can divide, a square, b square, c square for that upper bound. We will have the lower bound for the size of the, the image of the function. So now the problem comes down to how can we estimate given upper bound for the number of the solution to that equation. So the idea is to set up the set of the point and set of the plane in the space, and each of the solution will corresponding to a point plane incident. So we will try to rewrite the equations f x y z equal to f x prime y prime z prime as a point plane incident, and we need to set up the problem, and then we apply the rootnet incidence. In order to do for this problem, we need to classify the quadratic polynomials in two types: the one with one or two mixed terms, xy, xz, yz, and the one with all three terms. It's a little bit different in techniques, but basically the methods are the same. So, for example, I mean, for the first case, when you have only two or one mixed term, you are missing yz in this case. Then we can rewrite the equation fxyz equal to fx prime y prime z prime, like in the slide. And in this one, you try to put three variables on one side, another one to another side, and you can define the point set and define the plane set, and you can check that for each solution of the equations, it corresponding to one point line incident. It is kind of the technical, and if you are not familiar with this, you can see, I mean, somehow like, I mean, how the plane set and how the point set, I mean, come up. But simply, I mean, you put three variables on one side and another on the other side, and you can check, I mean, the number of the solution for the equation will be, without the exceptional, will be the incident between the point set and the plane set. Okay, so now before we can come apply for the rootnet incident, remember to check two things. First of all, about the size of the point set, not too much, right? And the second thing is check the number of the collinear points, and we need to make sure both of the conditions satisfy the rootnet incident condition, and then you can apply that, and it come up with the upper bound for the number of the solution for the equation. It should be E much smaller than A 2 over 2, 3 over 2, B 2, 3 over 2, and C over 3 over 2. And you divide over A square, B square, C square. You have a lower bound for F, A, B, C. Okay, it is a required lower bound. And you can do similar way. You can do it in a similar way for the second case, when you have all three mixed terms, xy, xz, and yz. You rewrite the equation fxyz equal to fx prime y prime z prime, and you can rewrite it as an incident between the point set and the plane set. Between the point set and the plane set, check for the condition of the rootnet incident, and we have that upper bound for the number of the solution. And again, I mean, divide that number for A square, B square, C square in the Cauchy-Schwarz inequality that we mentioned at the first step of the proof. We have the lower bound for F, A, B, C. Okay, so basically we have done with the proof for the three variable expander, three variable quadratic polynomial. And if you follow the line of the proof, you also can prove that A plus A square is bigger than A to 6 over 5, and it can be applied the same way. I will skip that part in the proof, but it's exactly the same way. You need to set up the number of the solution for the equations, and you set up the point set, you set up the plane set, and checking the condition for the rootnet incident and apply that. Okay. So let's move on to the four variable expander for the finite case. And in the paper by Dong-un, Mozarat, Thang, and Vaculescu, they show several results. The first one is improving the previous result by some authors. When we talk about the curve distance, A minus A power 3 plus A minus A power 3, right? And we have the upper bound for that set is at least A over A to the 8 over 7 when the size of the set is small. They also classify some other type of the four variable expander, the similar type of that, and more general forms is when fxy be the quadratic polynomials that depends on each variable, and it's not of the with the form with the additive form. Then we will have the some product type estimate, and more specific, it will be the max of a plus a, or f of a is bigger than a to 6/5, and it's a more quantitative versions of this result, and generalization is also can found in previous reference. Okay, so it is a summary of some 4 variable expander given by Dong-un, Mozarat, Thang, and Vaculescu. The things that I want to ask here is some problems. It should be interesting to look at this few problem. The first one will be classified on 2 variable expander. We have a partial result, for 3 variables, and the most interesting case will be for 2 variable expanders. The second problem may be easier than the first one, is to break the threshold 3/8 for 4 variable polynomial expander. And the third question is looking at the determinants and the permanent as an expander, and how strong that we can prove for this type of the expander. We know that the determinant and the permanent are expander. We have some related result for that, but we believe that it will be much stronger expanding function. And the fourth question will be the weighted version of root-nap incident. If we can have a good weighted version of root-nap incident, many applications will follow up. Yeah. So thank you very much. That's all for my presentation, and looking for the question or comments.
Yes, thank you very much. Question for speaker, please.
I have 2 questions. First of all, I don't understand what do you mean by weighted version of root incidence, because you can approximate any weight by characteristic functions, or you want much more precise bounds. I don't understand.
Yeah, I think we have some kind of the weighted version of the root-nap incident. Even in his paper, I think he mentioned about that. But I think that version of the weighted version is not strong enough for some application. So
what do you want to control here?
Okay, we want to control when the case that the point belong to, we have multiple point and multiple lines. Yeah. So the point and the line can be repeated.
So I see.
Yeah.
I see.
I think
okay.
For the set is very nice, so we can say that the upper bound also depends on the L2 norm. So the question is that can we say when we have a good L2 norm of the multi-set, so can we get some upper bound for that incident?
Yeah.
Okay, so another question, maybe stupid one. So you have some bounds for quadratic polynomials. Do you have asymptotic formulas in this case? I don't know, for large sets or not for large.
I'm sorry. What do you? Can you repeat that?
Do you have any asymptotic formula here? The numbers of solutions equals the main term plus something.
I think for 3 variables, I think I did this some time ago with Do1 and Julian Shen, I think. But for 2 variable, I don't know.
I don't think so.
Thank you. Thank you very much. Very interesting.
Thank you much. Any other questions? Ali, you have questions?
Yeah, thank you very much for a very nice talk, Vinh. I just have a very small comment, because for your second question, break the threshold 3/8. We know that if, say, A is larger than root P, then A minus A over A minus A fills up the whole FP. Doesn't that classify as this?
Polynomial, I suppose.
It is the polynomials.
Yeah, sure.
let my question will be very concrete. Suppose that we have a set of size epsilon times square root of p. Can you obtain something about a minus a over a minus a?
Yeah, but we want to look for the polynomial, not the rational function. We break the threshold p over h if we're looking for a rational function. There's some result already.
Okay, yeah, sure. Okay, thanks.
Yeah, thank you.
Any other questions? Okay, so if there are no other questions, so thank you very much again.